Hi guys. Okay, today I posted the lab 1 instructions, and this video is basically just reading you the instructions. We went through a little bit of this in class, right? And so we're using the MT cars data set, pretty traditional data set to start with. I renamed it car because I wanted to keep you on your toes. And then we looked at the scatter plot, and we talked about, we see a strong negative linear relationship here. And then we talked about fitting the linear model. And I can't remember how far we got. So we looked at the summary of the model, and we kind of said, okay, this stuff, I just want to make sure that you can see what I'm seeing here. Got my other screen here. So we're going to ignore kind of this output for a little bit longer. We'll get there. And then, man, we did a lot. Well, that's good for us. And then we added the line to our plot using the abline command, or AB line. And then we ended here, right, where we said, okay, we're going to add the residuals from the model because they're stored in that model. I'm going to take them from the model and I'm going to append them to the car data set, because that way I can kind of work with both. And same thing with the fitted values. Okay, so the instructions that I'm about to go through are also here in the PDF that you have, right? But I think I'm going to switch to our studio now and show you from there. Okay? Same document. I posted both the RMD file as well as the PDF, just so, oh great. My internet connection is unstable, it says. Guess we'll see how this goes. So if I go here, and I'm just gonna try to make this as big as I can. I'm on my tiny laptop. I don't think I can go any bigger without losing some stuff. Okay. So this is where we ended off last day, as we added the residuals and the fitted values to the car data set. So if we look over here at the car, I think this is the car data set. It's just catching up. At the bottom here, it doesn't want to show, just does not want to catch up, I guess. Okay, I had to pause it for it to catch up. Hopefully I'll try to remember to keep an eye out on this end here, make sure it's all good. So we have the residuals and the fitted values, and what I tasked you with at the end of last day was make sure that those residual values and the fitted values, remember, fitted values are just the predicted values, make sure that those values actually match the row that they were appended to, right? Remember, we took them from the model and we just attached them to the data set. They're not necessarily the same. They will be, because that's how it's laid out. But we just want to make sure, right? And what we're about to do, when we're confirming that the residuals and the fitted values are good, that they seem to match the data set, that's not part of your analysis. Right? Looking to make sure everything is doing what you assume it's doing, right? And so so I want to show you how to do that, but that's not something that you would show me in the future or show anyone else. It's just one of those background checks that you're going to run and just confirm that everything's attaching the way you think it does, okay? And like most things programming, my way is not the fanciest way or the most efficient way, or even, I don't know, even the fastest way probably. But it's one way of doing it, okay? And so I encourage you to check it out, check out other ways that you could do it. And that's how you're gonna get better, right? Better than me. But I also want to give you kind of the most basic jumping off point, right? You need to know something in order to improve upon it, right? And so I just want to, I try to always use kind of the simplest version. May or may not feel like it, but I try. Okay, so we have the fitted values, which are the predicted values, and we're going to confirm the first few fitted values in the residuals. Now, I like to use the cable library, which if you don't have cable extra and it has to be spelled exactly like this, then you would need to install that library first, which you would do by install.packages and then in quotes, lowercase cable, capital E extra. Okay. So you only have to install cable extra once, and then you should just be able to use the library command. Notice that there's no quotes in the when you call the library. And that's just, I don't know, a weird quirk, I guess. But once you have the package installed once, then you can comment it out, right, and not show it. So what I'm going to do is, because the car data set is quite large, right, we have expanded it to have 13 variables. So instead of showing the head, which is usually the top 6, but I'm forcing it to be the top 3 because I don't want to do 6. I only want to do 3. So I'm manipulating a lot of these commands. Okay, so what I want to do is introduce, if you haven't used it already, is the data. So the general data, and then in square brackets, you can have the row and then comma the column numbers. And that would allow you to access specific rows or columns or both, right? And so if you want all of row 4, for example, and all of the columns, or sorry, only row 4 and all of the columns, then you would say the name of your data set and then 4 comma blank. Okay, so now if I say that I want to access the 1st, the 6th, the 12th, and the 13th columns, right? And how did I get those? I got those from here, make sure it's catching up, because I want the miles per gallon, that's the 1st, and then 2, 3, 4, 5, 6, that's the WT. I also want that information there because that was my explanatory variable. 7, 8, 9, 10, 11, 12, and 13. I forgot my, well, I have my fancy webcam, but I forgot a USB dongle, so I can't actually connect it or use it. So I have to have a weird light bulb here. So I have shadow. Anyways, you'll survive. So how do I specify that those are the only columns that I want? Okay, so let's build out from inside here. I say my data set is called car, okay, and I want all of the rows, right? So I leave the row portion blank, and then for the columns, I'm telling it, okay, here's a list of 1, 6, 12, and 13 using that concatenate the C, and so here are all the columns that I want. Don't be confused by the C. The C happens to be in the column, but the C is concatenate, and that's what we use to make a list, okay, and to feed it a list. So then if I only run this, okay, scroll up here, notice how if I ran car, square bracket, nothing, comma, so all the rows. So notice how it gave us all the rows. And then you can confirm, right? As you're building up this code, I would never build this from scratch. I would build it up and check it, make sure it's doing what I think it's doing until I'm happy with it. Okay, so here, this is the information that I wanted in there. But now what I want it to do is the head command typically only gives the first 6 rows. I think it's 6. But you can specify how many rows by as an argument. So then if I say the head of car, so the data that I want, comma 3, okay, so the head command with 3 gives me just the first 3 rows. I think you can use tail too for the last 3 rows if you want to get weird. And then if I wrap this up, because this is a table here, if I wrap it up in cable, in the cable command, what that does is it produces markdown code. Now you don't have to do anything with it, but we can look at it. And this is kind of my cheat sheet for, so if I run that code here, it produces a table. So it produces a table with all this markdown information, right? And so it has the data that we want in the table, but this is also the formatting for the table. So kind of a cheating way of making a table in Markdown is if you have a table and you put cable around it, and then you can just steal this code. So in theory, if you wanted to, you could copy this. Let me see if it's catching up here. Okay. Don't include the carets here because they don't mean anything in Markdown. But what you could do, even though it's pretty messy, you could include the Markdown code in the Markdown section of your document. So in the white section of your document. Remember, the gray section is your R code, and the white section is your Markdown code. Okay. So now, if I were to knit this, it should produce 2 tables that look the same. One is produced from this cable command, so you don't actually have to do anything. It'll just produce the table using Markdown. And then the next table should be from this code that we inserted. It says my internet connection is unstable again. I don't know why. It's got everything it wants. Full bars, I mean. Let's see here. Let's see. I guess I should have paused it. Wow. 95%. Come on. Where is it? I really should have paused it. Feels like I've waited too long now to pause it. Note for next time. I'm not going to knit it anymore. Okay. While it's working on that, because it's really just to show you that you're doing the same thing twice. Oh, here we go. Okay. So if I scroll down here, oh, what the? it didn't do it. Now that is surprising and also disappointing because I don't know why it didn't. Cable command made the table as I expected it to. And then the markdown, I must have not copied all of it or something because it's not giving the table anyways. Oh well, lesson learned. No big deal. You shouldn't do that anyways, so it's fine. Okay. So I'm gonna undo that there. Okay. It was just supposed to show you that it's just generating markdown, but anyways, doesn't matter. I'm not exactly on my A game today, so oh well. Okay. So in order to check our residuals and our fitted values, we're going to start with our fitted values because remember, we need the predicted values, which are the fitted values, in order to find the residuals. So we'll start there. And in order to find those predicted values or the fitted values, we need to have the coefficients from the model. Okay, and so we can access the coefficients in a similar way. So in the mod object, if we do $ coefficients, then there are two coefficients in our case, right? And if we look at the mod object here, then the coefficients, there are two of them. One is 37.29 and one is negative 5.34. So this is the first one and then the second one. So mod coefficients and then square bracket 1, because there's only one row, so it just looks for the first item or the second item, as opposed to the row, comma, column setup. Okay, but very, very similar. Right? If I run mod coefficients 1, then down here, it produces the intercept, right? Notice that this is has more decimal places than what we have here, 37.29. It's obviously the same number, but let's use the 37.28513. So let's use the mod $ coefficients 1 as our intercept value, right? That way we don't lose any decimals, right? We're not rounding. Same thing if we take the second coefficient, that's the slope, right? All right, so now things are gonna get weird, but also repetitive, right? So in order to find the fitted value, what do I have to do? I have to take my intercept plus the slope. Always use a plus because if the slope is negative, then plus adding a negative value is the same as subtraction, right? Hopefully you know that. That is subtraction. But anyways, and then I need to multiply it by the WT, so the weight of that car. Okay, so for that observation, so car 1,6 pulls out what? It pulls out only row 1 and only the 6th column, right? Which is the weight for car number 1, okay? Or the first line. Now, R is clever enough to know order of operations. So technically, you know, you should put brackets around your multiplication first, and then add it to, but R is good with order of operations. And so if you hit enter here, then you get that same value. So we can check that for row 1, 23. I am going to pause the share and re-knit this because I only want this good table, not this wacky table that I was trying something with. So just be right back. Anyways, so I guess you wouldn't miss anyways, but anyways, okay. If we put in the weight 23.620, then the predicted value is 23.28261, which if we scroll down here is exactly what we found by plugging in those values as we just did, right? So taking the car data set, the first row, the sixth column, okay? And notice that that's not going to be the sixth column of this, right? It's from the original data set, okay? And then we can confirm the other two. So the next two should be 21.91977 and 24.88 something. And if we scroll down here, those both look the same, right? And so that's good. So I'm satisfied that we've confirmed that the first three fitted values are exactly what we expect them to be. So I'm willing to assume that the rest of them worked as they should have as well. Okay, so that's fair. You can do that. Sometimes it backfires, but I think it's a safe assumption. Okay, so but it's always good to know how to check stuff, right? Did it work as I expected it to? So now that we have the fitted values, I want to check the residuals. So feeling pretty good, they should work, and they do, right? And so, and I'm just going to stick to the PDF here, I think. Maybe I'll make it bigger. There's a thought. Oh. Maybe. If it'll let me. Whoa. Okay, I guess that's kind of fun. It's not really what I wanted though. Okay. Catching up. So to check the residuals, and another thing that I did here was I did include the R code or the markdown code, which is actually LaTeX, not to be confusing here. But I included the LaTeX for writing things like E subscript I is Y subscript I minus Y hat I, right? And let's go back there and see. Okay. Let's see here. Okay. Because it's, again, nice to have a jumping off point for writing LaTeX here. So if you use a $sign, and sometimes I'll use just a $sign, so $1 on either side of the LaTeX code. And what that does is it doesn't put it on a fresh line, right? It just incorporates it into the text. Whereas if you do $2 then it'll put it on a fresh line, and that's what I wanted, and nice and clean. So E and then subscript I, so you do a subscript with an underscore, and if you have more than one thing in the subscript, then you have to wrap it up in brackets, but you can Google your way to that. Okay, equals YI minus, and then the slash hat, and then in curly brackets, whatever you want the hat to be over. Okay, so just an example of some LaTeX code, and it's just typesetting for math specifically. Any typesetting, but it's most useful for math. Although once you learn LaTeX, you're not going to want to use Word ever again because it's so frustrating. Okay, so to check the residuals, okay, I want from the car data, I'm taking the miles per gallon column, right? So $MPG. And then when I do a square bracket 1, it's telling it to only look at the first value of the miles per gallon column. And then I'm going to do the same thing minus the fitted value of the first column because I've already confirmed that those match up. Okay? And then I do the same thing for the second row and the third row, and they work out. They're all the same, and you can check it. but I'm satisfied that the residuals and the fitted values do in fact match for the first three, and so I'm willing to go ahead and assume that they match for the rest of the data as well. Okay. So this leads us to our residual analysis. So now I'm feeling comfortable and I want to do my residual analysis, which means I've fit a model, which we have a model, and now I want to check the assumptions. Okay. So we need to check 3 assumptions before we proceed with the model, whether that's, publication, which not really, but, it can be on a scale, right? Using it and proposing it to your client, that kind of thing, right? And so we have to check our assumptions. Now, the first assumption is, of course, linearity, okay? And I talk about each of the assumptions later if you want to read that, but I'll just talk about them here. So the linearity condition, we already checked it with the scatter plot, and you wouldn't fit a straight line to something that didn't look like it could be fit by a straight line. Okay, but now we want to get a little bit more, we want to confirm that the linear model was appropriate. Okay. The next condition we're going to check is heteroskedasticity, which is fun to say, but also really hard to say. Heteroskedasticity, or constant variance. So what we're checking for here is you want to have the same even random scatter around I don't know what happened. It says it's still recording. I'm not sharing my screen. It all went away. Okay. Okay. Let's see here. Okay. Sorry. I think it's all back to normal. All right. Let's see here if I can get my groove back. Okay, heteroskedasticity. There we go. So if we have really, really tight scatter around the line for only a small region of X, then we would have really good predictions for that region. Okay, but then if the scatter starts getting wider and wider and wider, with wide scatter around the line, we would have weak predictions, right? Poor predictions, unreliable predictions, and so that's not good, right? And especially if we're trying to report an overall reliability of the model, right? So or a goodness of fit for the model, then that's not going to apply, right? Because it doesn't specify, oh, for these values of X, it does a really good job. And then for these values of X, not so much, right? Because it would just give you an overall value, and that's not very useful, right? And so we have to have constant variance in order to avoid that. And then the last condition we need to check is that we have nearly normal residuals, okay? Which you probably have a pretty good idea of how to check if you have nearly normal residuals, and you're absolutely right. We can use but let's go through and look at the graphs that we use. In fact, the linearity and the heteroskedasticity assumptions, we actually can use one graph to check both of those, right? And so what we're going to look at is we consider a plot of the residuals against the explanatory variable. And this is the reason why I wanted to attach my residuals and my fitted values to the data set so that I could map them against each other. There's other ways to get around that, but it's good practice. Now I fit against the explanatory variable. I've seen against the fitted values, and there's lots of different things that we could consider, but for now, let's just focus on the explanatory variable, right? Just for simplicity's sake. Okay, so I can make the plot. If I run the plot here, then I get this plot, which is the one I had in the bottom corner, but we weren't using it quite yet. And what we're looking for to check the linearity condition is just, do you have random scatter around 0, right? And so to help us see where 0 is, right? Because here we've got our residuals on the y-axis, and I've got my explanatory variable, which is my weight, on the x-axis, and here's 0, and I just want to add a line at 0. So an AB line from 0 to 0, and as long as the plot was the most recent thing you did, it should add the line at 0. Okay, so now I can see, okay, it's basically a magnification of the relationship that we saw in our original scatter plot. Okay, if I'm being very, very, very picky, I would say that there is kind of this bend in the data. Okay, not enough for me to be concerned about or even potentially pursue a different model. It's just not a very good model. But in general, I would maybe say that this is sort of random scatter around 0, right? We do have this pattern here, so we'd want to mention that. You don't want to be overly picky, but in this case, it's worth mentioning. And so what I said was, we look for constant scatter around 0 with no distinct pattern. In this case, the residual plot shows a slight smiley shape. It keeps booting me out. Share screen, share. But it claims it's still recording, so I guess that's good. Okay. So, where was I? Oh yeah, so this slight smiley shape is indicating that there's some non-normality, which means we should probably consider a different model. We don't have any up our sleeves yet, so that's fine. And then, so what I said was, for now, we will assume that the linearity condition is met. And it's okay if it isn't. Just means you have to find a different model. Now, for the heteroskedasticity, so the constant variance condition, our data points should show constant variance around the fitted line. And if they do not, right, here's the explanation, right? Then we have strong predictions and weak predictions all on the same line, and it just makes a big mess, okay? And so we can check this assumption with the previous plot of those residuals against the explanatory variable, which is this one. a lot of the time you might see a funnel shape or any sort of like fishy pattern, kind of like boom, 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 boom. Those would be non-constant variance. Okay. Right, we have this kind of, okay, all the points are above the line, and then they kind of, here there's random scatter, and then they're back above the line here. So it would be some non-constant variance or some heteroskedasticity, but I'm not sure it's enough to worry about. In this lab, all I'm concerned about is you getting comfortable with looking at these and landing on some sort of conclusion. Is there non-constant variance, or is there constant variance or not, right? And so just kind of argue it either way. Okay. I concluded with saying that the scatter around zero is random enough to satisfy the constant variance assumption. That's what I landed on, and that's going to be my push. The last condition that we're checking is the nearly normal residuals. And of course, you can make a histogram of the residuals, and I'll try to produce that here without my computer booting me out. It looks approximately normal with maybe a little bit more of a tail on the upper end, right? Histograms are good because we're so comfortable with looking at them and reading them. But in terms of publication and just kind of in your reports, you should use a QQ plot. So you're going to use the QQ norm command and on the residuals, and you're going to get this QQ plot. And then we always add the QQ line, which is a line where the perfect normal distribution would be. So any points that are on the line Okay. That's like the third or fourth time that it's kicked me off. It's so annoying. Okay. Try to wrap up here. Sorry, guys. Oh yeah, so the line is the perfect normal distribution. So all the points that are on the line follow the normal distribution as they are expected to. We do see some liftoff here. Oh, I see my screen is lagging here. Oh man, okay. So it looks like we're back. We do see some liftoff in the tails, which is perfectly normal. This might be a little bit of a concern, but not really, because we have such a small sample size. Okay, and so, and this liftoff that we see here is the same as that slightly longer tail that we saw in the histogram. Okay. Oh, let me pause this. Okay. So my argument would be that because we have a small sample size, 32, we can assume the residuals are nearly normally distributed, right? For smaller sample sizes, we expect to have a little bit of kind of non-normality in there just by chance alone, right? Okay, so I'm leaving you with some exercises, or one exercise really to do on your own. You're going to start a new markdown document, or just make a copy of this one if you prefer. And then what I want you to do is I want you to use the same data set that we've been using to answer these questions. You're going to knit to PDF your answers and then submit those answers to Moodle. It's kind of a choose event. You're going to make up a question that you want to answer involving two numerical variables in the empty cars data set. Okay, I want you to identify the response variable and the explanatory variable. And it really doesn't matter if your question makes sense or not. You might ask, you know, does the, what are some of these variables here? Does the drive ratio or whatever the DRAT was, does it affect the horsepower, for example? That might not make sense, but that's okay. Let me just pause here. Okay, sorry, there's a disruption. So make up any sort of question. It doesn't have to make sense. I kind of chose one of the more obvious response variables, which was miles per gallon. Feel free to use miles per gallon as your response, but pick a different explanatory variable, or just to show off, you know, try something completely different. Make sure that they're numerical variables. Okay? And then I want you to tell me what the response variable is and what the explanatory variable is. Okay. I just might get through this once and for all. Once you've decided your variables, I want you to make a scatter plot just like we did together. And for this exercise, it really does not matter if you have a nonlinear relationship or if you have a linear relationship. Just keep that in mind as you fit your model, right? And then next thing you're going to do is actually fit the model, and I want to see the output summary. Okay, so the output of the model summary, okay? Just like we did together. Then I want you to show the scatter plot with the linear model applied, just like we did together. Then I want you to check the linearity condition and talk about why or why not that condition is met. Okay. Then check the nearly normal residuals condition again. Talk about why or why not, or why those conditions are met or why they're not met. Okay, so it doesn't matter if they're met or not. That's not the exercise. The exercise is just talking about them and paying attention to the details. And I guess I skipped the heteroskedasticity condition, I think, but check all three conditions, basically. And then the last part of the exercise that I want you to do is just briefly discuss whether you think this model is appropriate and or useful, right? Maybe the variables that you looked at, maybe there's nothing useful there. And this is just for you to kind of talk about your variables that you chose. Maybe it's not a good model, right? Maybe it wasn't linear to begin with. So this can be as obvious or as deep as you want it to be. But I want it to just be a brief discussion, and it's very open-ended. And I just want to kind of give you a chance to tell me things that haven't come up already. Okay. So sorry it took so long, but here we are. Hopefully it's not too choppy, and good luck. See you next week.